Okay. Okay. Hi, I'm Mike. I'll be talking about null tests, which is basically how we look for systematic errors. As I said, looking for signal in all the wrong places. Something I'm pretty proud of. I led the team that did the shear catalog paper for the SV data. It came out about 1.5 years ago, and I'm very proud that we have a whole bunch of plots, none of which have any science signal in them. Every single one of them, we removed all traces of something anyone could do science with. So first, Rachel just talked about a lot of this, but I'm going to just go back over it again quick. So statistical errors are any kind of errors that have 0 expectation value. So we think of them as kind of going plus and minus kind of equally in some kind of distribution with 0 mean. And importantly, as you take more data, they tend to get smaller and smaller, right? The root n kind of effect. Systematic errors are errors that have non-zero expectation value. As you take more data, they don't tend to get smaller. And probably, if you want my opinion, LSST cosmology will be systematics limited. We have very, very low statistical errors. And there's going to be a lot of sources of systematic error, and my guess is that that will dominate our error budget. At the very least, systematic errors will take up all of our time trying to figure out to get them as small as possible. So either way, they're important, whether they end up being the dominant source or not. So just kind of terminology, statistical errors are usually called noise, and systematic errors are usually called bias. So these terms are quick, yeah? It's a bias that comes from noise, actually, and it is in a very particular way, and I'll actually mention it again. But that's a good point. Yeah, so it is a bias. Noise is an adjective there, not the noun. So this is kind of the fundamental way of thinking about things. So you have some measurement. There's a truth value to it that you don't know. It's what you really want to know, but you don't know it. There's some noise on top of that. Right, some random fluctuation, and then potentially there could be a bias. Hopefully not, but often there is. Right, and as you take the expectation value, so if you look at kind of this measurement averaged over many galaxies or averaged over many clusters, whatever it is you're doing with it, the expectation value is going to be the noise goes away, so you end up with just the true value that you want plus the expectation value of your bias. And that's a problem because you only have access to your measurements, so this bias is messing up your answer, right? So null tests are a way to try to get at whether or not we have this bias that's messing up our answer, right? So the idea is that a null test is some measurement whose truth value is expected to be 0. So you want to arrange some kind of statistic that if your experiment were working perfectly, you would get 0 for your answer. Right? And if your experiment's not working perfectly and there's systematic errors, those systematic errors may cause a bias in your measurement, in your null. Right? Importantly, it's usually difficult to get the bias in this measurement to be the same as the bias in your normal measurement, so it's bias prime here. Right? But some systematic error, if it exists in the real data, the idea is to try to make your null test to make it also show up at your null test. So if there is a systematic error, you get some bias here. And the converse of that is if there's no bias in this, hopefully that means that, at least for that particular systematic error you're looking at, the systematic error is not affecting your main measurement. Right, so this is what I just said. So the goal is to design tests so that if bias prime is not 0, is about 0, that implies that the bias in your main measurement is about 0. Or if you measure it to be non-zero, or if it's not 0, then you'll find that out by noticing that the value of null is not 0. Okay, so designing null tests is kind of an art. It's something that takes some practice, and we'll do some practice here. I have a few examples for you guys to break up and think about, but first I'm just going to give you some design principles that you can kind of have in your heads as you're trying to come up with some good null tests. The first one is if a systematic effect that you're worried about has a dependent relationship with some variable, but the science does not, then binning your data with respect to that variable is probably a good null test. Okay, so if you, you're worried about the time of day being a problem, right? And you think your science doesn't care what time of day it is because it's cosmology and it's galaxies far, far away, right? Binning your data in terms of time of day may look for whatever the systematic is that happens, on some cadence with, with the sun or something, right? That's the idea there. Principle number 2, correlation functions are your friend. Lots of things you can correlate between, 1-point correlation functions, 2-point correlation functions, lots of different kinds of correlation functions. If you can correlate two quantities that shouldn't have any dependent relationship if your experiment were working right, but would maybe if there were some systematics, those can be good null tests, okay? And then the other one is if the science should be invariant with respect to some variable, like the science doesn't know, it's kind of like that time of day thing. If the science doesn't know about some variable, then you can sometimes split on that variable. So rather than binning with respect to time of day, you may say like all the things taken in the afternoon and all the things taken in the morning, the difference in the science result between those two should be 0 because the science doesn't know about morning and afternoon, so you can maybe take the difference. Sometimes you may not have enough signal to noise to do a real binning, but just splitting in half and looking at differences, those can be good null tests. And then the last one is be creative. Like sometimes these systematic errors, you can kind of follow through a chain of reasoning and come up with some fairly non-obvious ways that that systematic might show up in something that should be null in your science. So try to think of kind of maybe not so obvious consequences of your systematic errors, right? So it's kind of you can think of like, it's the flip side of designing good experiments. So normally the null hypothesis, right? We think of like rejecting the null hypothesis. Here, you're trying to you are sort of trying to reject that, but you hope you fail, right? The null hypothesis is that you have no systematic errors, and you're trying to reject that by showing that you do, and in fact, you're actually hoping that you fail in that process. Okay, so here's our first example. So I'm going to have you guys all split up into groups and think about it for a bit. So the PSF. So Rachel talked about the shape of the PSF. We care about it a lot for weak lensing, but other people do too. So this is not purely a weak lensing question. So the PSF is partly due to telescope optics. So it varies for very normal physics, ray tracing kind of things through your telescope reasons. There's aberrations like coma and astigmatism, stuff like that, which vary across the focal plane. And then there's other parts of the PSF which may be more stochastic, still have some variability, but the atmosphere tends to be more of a stochastic process, less coherence across the telescope. On any one exposure, it still does, though. So in any case, it varies across the field of view. So design a null test to see if the code for estimating your PSF is doing a good job of accounting for the variation of the PSF across the focal plane. So split up in your groups, and I'll give you a couple minutes, then I'll ask for ideas. Okay, what do we got? Who has an idea? Have an idea here?
Well, if we play with comma and acting mechanism, for example,
Mm-hmm.
in the model, then if the model is correct, and we compare with measurements on simulated,
Compare to simulations and see if the way that you have coma looks like what, say, Zmax or something spits out for your telescope as being the way your telescope is supposed to have coma. Is that the idea?
no, not really.
No? Okay, sorry.
If your PSF estimation code is correct,
Yes.
then it should not, the difference between the PSF estimation code, the result for the PSF gives, and the PSF you measure on simulations
Okay.
should be 0. So that's not test.
So his idea is to take the measured PSFs and subtract simulated PSFs for the telescope that you're making, and the difference should be 0. The problem with that...
And you move the parameters and you see whether it's stable.
Right. So the problem with that is every exposure has different parameters. So the coma and astigmatism not only vary spatially, but also vary temporally. So as the telescope tips around and different things.
We can sample and we can bin.
Maybe. What else we got? Other ideas?
You could split the data into pieces like the left and the right side of the focal plane or center and edge and so on. Compare an object, the same object that was imaged in different regions.
Take a galaxy, you mean, or
Yeah.
so see if a galaxy has consistent measurements after correcting for the PSF as a function of focal plane. That's great. Yep. That's good. Yep. Another one.
Could you do just cross validation? I mean, you remove 10% of your star of your training and see just if you can construct
Excellent.
the size of the PSF.
Yes. So his idea is to reserve some stars that you know are point sorted, are good supposedly samples of your PSF. Don't use them in your fits. Don't use them in your PSF reconstruction, and see if your PSF model produces a good answer for that at those locations. So to make that a null test, we would want to take the difference is what we care about, right? So the difference between your measured stars and your model stars as a function of position. Good. Other ideas, anyone? That would be nice, but no. Yes, if there was radial symmetry that would help us out here, and typically not. There's some component that's radial symmetric, but there's too much that's not for that to be useful. Anyone else?
Looking at the average ellipticity
The average ellipticity of galaxies, so just take the mean
you just extract your ellipticities, the best that you have, and you see that
of the stars, or of what? Ellipticities of what?
anything.
It matters.
If you have, for instance, an elasticity measurement that is consistent vertically on where you are on the focal plane, if there is this kind of component, you can see it.
Right, so you could do that with galaxies. So if the galaxies were corrected, you can look at the mean as a function of position on the focal plane of the galaxy. If they were incorrectly correcting for the PSF, there would be a bias there. That's good. Yep. Any more before I go? So I'm going to show you some from the literature. So here's one that is basically the reserve test that someone proposed. Right. So this is the difference between the E1 and E2 values of the PSFs between the model and stars that were reserved and weren't used in the model. So you can look at the difference there, and you can see there is some residual. It's not 0. This was a null test that failed at some level, but it's much smaller, say, than the raw ones. Another way that you'll see this kind of information displayed is as whisker plots. So there's a different set of data, but the same telescope. And we look at the differences and plotted them rather than as E1 and E2 separately. We draw what's called whiskers, and that's basically a stick that is the length is proportional to the ellipticity the magnitude of the electricity, and the direction is the kind of the orientation angle. John?
So is failing this null test the fact that those whiskers are not zero length, or is it that they have some correlation?
Both. So the ideal null would have been these would be all little dots, right? So zero length whiskers. And then to the extent that matters, now we have to look into the correlation of them and things like that. So
So spending random noise would not be as bad as having correlated PSF.
right. So if they were just kind of random orientations, that would probably not affect most science results as much as having correlations in them. That's true. Here's another one that no one mentioned. That's one of those kind of secondary or tertiary results. So tangential shear around the centers of all your pointings, right? So tangential shear is the shapes of galaxies oriented relative to some central point. Usually we do this with lenses, right? So we have big galaxies or galaxy clusters as our lenses, and we look for the tangential shear around them. This is the tangential shear in the SVDES data around all of our pointings. The center of every location we pointed the telescope during the observations, we looked at the tangential shear around them. And you see it's not zero, but it's kind of, this is more kind of the noise that this is pretty close to consistent with flat and zero. So this tells you that maybe that some of those other whisker plots don't affect galaxy-galaxy lensing, because this has got the worst possible center locations for this effect, and it's not significant.
Is this really a null test just of the PSF estimation, because you're also using shape measurement?
Right, that's right. So yeah, so if this were failing, you don't know who to blame, right? But it basically is telling you how much that particular systematic could affect this kind of a science result. So different kinds of science results may have different null tests that are appropriate for testing different systematic errors. So this would not be an appropriate one for people studying magnitudes or redshift or photo Z estimation or something like that. This isn't how they care about that particular error.
It also may be very sensitive.
Yes. It may be insensitive to that systematic, but it does tell you the extent to which galaxy-galaxy lensing is sensitive to that systematic, and that's what they cared about. So, they being galaxy-galaxy lensing people. Okay, here's another example that I will again ask you to brainstorm on. So this one, Craig Glage is highly familiar with. The brighter, fatter effect is when, as light is incident on your camera, it makes electrons. The electrons rain down from voltage and get caught into each individual CCD. As you start to get a lot of electrons, they start repelling the next ones down and push them out into neighboring pixels. So brighter things tend to get kind of a little bit bigger, so brighter, fatter, right? We understand it pretty well from lab tests, but what would be a good null test to see if we're properly correcting for this effect on real data? So how do we know whether we're properly correcting for the fact that brighter things have been kind of made a little bit fatter by Coulomb's law? Oops, what did I do? Well, think about that, and I'll try to see why the camera turned off. I wonder if I did that. There we go. Okay. Okay. Sounds like most people have maybe at least their first answer. So who would like to volunteer? No? Who has an idea?
So my neighbor is
Yes. Okay.
look at the same field with a different exposure time.
Different exposure time, great idea. So to see if you get the same sizes or magnitudes of objects, great, yep. When you look with more electrons versus with fewer electrons. Yep, great, yeah.
The problem with that is not with all the atmospheric variation, because you can have a variation of size which due to atmospheric variation, but not due to the exposure time.
With 15-second exposure, you have to
Yeah, well, no, seeing varies for 15-second exposure. So you would want to, so in particular, looking at the slope of sizes with some magnitude as a function of as a function of exposure time.
If you are doing the same thing with the fake star, like the example I guess for CFHT, like SNDice or something like that, you can do exactly the same thing, but with the fake star.
What kind of fake star?
I mean laser or something like that.
Nothing.
No, but
We don't have laser guide stars here on LSST. Yeah.
I would look at the theory of detection and plot the maximum flux versus the aperture flux, and then you can see if you're getting flux.
Good, right. So things that should be a kind of the same profile, look at the, say, aperture flux versus the peak flux, the central pixel, and see if the profiles are changing for some subset of some class of objects that you think they shouldn't change. Good, yeah. Been. I see. So if your object were oriented like in an E1 versus E2 direction, the magnitude of the effect may be different. Possibly, yeah. That's a good idea. I don't know. Yeah.
Similar to last one, we talked about holding back some subset of the stars. You
Uh-huh.
can put the stars in the bright ones and dim ones that you use to generate the PSF model.
That's right. So look at the sizes of stars as a function of their brightness, right? So the bright stars versus the dim stars, the seeing should be independent of how bright a star was, and so so looking at the difference of that. Good. Any other ideas? All right. So that last one is basically this plot. This is the difference between the PSF as measured from a real star minus the model, the difference between the PSF and the model, as a function of the brightness of the star, as a function of magnitude. And so you can see on the left-hand side, there's a big brighter, fatter effect. The bright stars, the real PSFs of the stars are bigger than the model PSF. And then as you get fainter, they start to become close to zero. This is the line. So we use stars out here for doing the modeling. We threw out all these stars to try to avoid the brighter, fatter effect. So this is actually not testing that we are correcting for the brighter, fatter effect properly. It's testing that we are avoiding the brighter, fatter effect, which was all we tried to do on SV. But ideally, if we're correcting for it, this would be flat all the way out to the bright stars.
Really dim end again. I remember seeing that the model actually gets bigger.
Yeah, I mean, so at the very faintest end, we're now into the how good quality PSFX is at measuring the model, and there's other issues that are going on. Yeah. That's right. So yeah, you can also do this as a relative error, and it looks very similar. But yeah. Well, so the t here is typically about 0.3. So that multiply this by 3 roughly to get a percentage or a fractional error. Yeah. That's a good point. So this doesn't so the fact that this fails doesn't necessarily mean that this is the reason, right? There could be other reasons that would cause this problem, and that's always an issue with every null test. Is when it fails, it may not be for the reason you think. And I will get to a whole bunch of list of caveats, and that's one of them. So that's good. Good to call it out. Okay. Just for fun, this is the shape doing the same thing. The brighter, fatter effect is not isotropic. It affects the rows and the columns differently, and which means it affects E1 and E2 differently. And in fact, E1 shoots way up. E2 never gets that big, but it does have some effect. And it doesn't level off at 0 because PSFX has issues. But small enough issues that this is actually not a big problem for us. Okay, good. Example 3. So this is something that Rachel mentioned. So one of the ways that shear estimation can go wrong is that some of the PSF shape can leak into the galaxy shapes, right? So you try to correct for the fact that there's a PSF and its shape has affected the observed shape. But not all shear estimation methods are perfect. Some would argue that none of them are perfect, including myself. But in this particular regard, design a null test to check if there's any significant PSF leakage of the PSF shape into the galaxy shape. Okay. Who has an idea? Yeah.
If I remember, for cosmic shear, the limit of galaxy should be 0. So if you have a limit not equal to 0, you have a problem with your PSF.
Good, yes. So one of the classic weak lensing null tests is to look for the B mode, which is the curl part of your shear field. There's a theorem in weak lensing that the shear pattern should be pure E mode, purely a divergence. And normally, most of the time, if you get a B mode, the PSF is the thing that people blame for it. So a good test, if you think this might be a problem, is to look at the B mode. If the B mode is 0, you're probably not leaking too much PSF shape in. That's good. Are there more direct ideas?
When you look at, so the star, like the sun is more or less bright. Can we look at those stars and get an average and see what is the image of the star?
Right, so you can get basically a shear, quote unquote, for all your stars and see if those are 0 the way they should be, right? So not all methods can do that, but yes, definitely some shear estimation methods allow you to get a valid measurement of stellar shape. Some of them become undefined because of the way it works, but some definitely don't, so that works.
That doesn't tell you whether it's a PSF.
True. So it doesn't tell you whether your galaxies are affected, it only tells you whether your stars are affected. But if that fails, that would probably mean there's a problem. That's right. Someone back here had, yeah?
So check around random points in
How do you mean?
Versus, like, if you're looking at lensing versus nearby galaxy cluster, look at random points in the sky.
Oh, I see. Do like a tangential shear around random points. Yes. That one turns out is a little bit problematic because for subtle reasons, we don't expect that to be null because of your masking. So your masking can impart signal there. And so the standard measurement that we usually do is actually the tangential shear around lenses minus the tangential shear around random points. And it's not quite a trivial subtraction by 0. But that's a good idea. So certainly if you make that measurement and there's something obvious there, that could tell you something about whether or not there's a problem. Because it should be a very subtle effect, but if you see a subtle effect, it may not indicate a problem. But it's always good to make that test, and sometimes it can tell you something useful and possibly about this. Yeah. Others, yeah.
Look, correlation, your PSF residuals is a focal tape, and it should be 0 normally.
Say that again, I'm sorry.
You should look the correlation in the focal tape of your PSF residual, because due to the fact that at the end for cosmic field you will look at two-point correlation function, you don't want to have a correlation between PSF modeling. So if you introduce correlation due to bad residuals, you will propagate that to the methodology. So at the end you should look. I guess you should this kind of stuff for DS. So.
Right. So I think what you're suggesting is we can make the PSF residuals, and in fact the PSF shape, and correlate that with galaxy shapes, right? And so that cross correlation is going to tell you whether there's some leakage, and that definitely is something that we do, and it's a good one. Yeah.
Could you look at the galaxy shape as a function of distance to the stars that we use for modeling the PSF?
Right. So that's good. Yeah. So galaxies that are closer to one of your test stars may have a better estimate of your PSF than ones that are farther away. It depends on what your PSF model is, whether that makes sense as a diagnostic, but certainly something that used like a nearest neighbor kind of model. You would expect the model to get worse as you got farther away from the nearest star that could be used as a test. So that definitely is a good one. Yeah. See if right, so bin on seeing. So look at the maybe high seeing versus low seeing and see if there's a systematic difference, because there shouldn't be. That's excellent. Yeah, that's a good one.
Yeah, there's a tangent on that, is to equate the PSF on the real image, because we know how to do that.
Right.
So, and then see whether the galaxy shapes are free.
Good, right. So you could take some fairly high seeing data and intentionally degrade the data, and you know what your right shapes are, or some mean shear across a field, and see if you get the same mean after degrading your shapes. So one of the things that you need to worry about with both of these kinds of tests is the thing that Rachel said, is you don't expect the same answer galaxy by galaxy. That doesn't imply any bias. What you care about is things like the mean. So statistics of your sample need to be consistent. So it's just, those are both good, but you just need to be careful of how you design that null test to make sure that you're only looking at shear responses, not galaxy by galaxy shapes. But those are both good. Yeah. Anyone else? So the easiest one, I'm surprised no one said, was you can just bin your galaxies by the PSF that was used to work on them. So this is a plot of the mean shape as a function of the PSF E1 and E2. And they should be flat. There should be no residual correlation between the input, this is what we were worried about, the PSF shape, and the output, which is the galaxy shape. So this is the most direct method, the most direct null test for that. This one was mentioned. This is the cross correlation between stars and galaxies. That's the red curve up there. The blue is the autocorrelation of the stars themselves. So they're supposed to be big and way up there. The reds are supposed to be close to 0. Turns out that for very subtle reasons, they're not exactly 0, and you can calculate the leakage as a function of those two curves. And you can look at the paper for the details of why it's not quite 0. It's not completely intuitive, and I don't really have time to go into it. But the red things should be small and close to 0, and from that you can calculate the alpha, which is this bottom thing, and that comes out to be completely consistent with flat and 0. So those are two good ones, but there's tons more as you guys came up with, which is great. Okay, example number 4. This is the last weak lensing related one. Rachel talked about noise bias, right? So at low signal to noise, one of the problems that you can have is that the noise in your data now goes through this nonlinear process of shear estimation, and any nonlinear process can take pure noise and turn it into a bias. This is what we call noise bias, right? And so the question is, what null test would check to see if we have any residual noise bias in the galaxy shapes? Okay, so talk among yourselves. Okay, in the interest of time, I want to cut it off. I apologize. Anyone have an idea? Anyone? Yeah. Good idea. This is the mean ellipticity as a function of signal to noise. Unfortunately, this is not an answer. But it's a worthwhile test to do. It's just not actually testing noise bias. It's the most obvious thing that we thought of. And after we did it, we realized that it's not actually testing what we care about. Well, this is testing an additive error as a function of signal to noise. But noise bias is, in fact, a multiplicative error. And if you multiply all of these guys by 1 plus m and m isn't 0, you don't get something different than 0. So good idea, though. Anyone else? Yeah.
Maybe you can degrade your image by adding noise and you get the same shares.
Good, right. So it's similar to the idea about the PSF. So you can take a high signal to noise image, degrade them, and see if that gives you this consistent answer in terms of your mean shear, something like that. Great. Yep. John, did you? Okay, so tangential shear around lenses at, say, high signal noise and low signal noise and see if you get the same answer, that kind of thing? Yep, great. That's what this one is. So this is splitting the source data on by signal to noise. So the high signal noise galaxies and the low signal noise galaxies around some set of lenses that, for this plot, we don't actually even care what they are. You do need to be a little bit careful. Because this signal is a function of redshift, the redshift distribution of your sources. And so the thing that Joseph did here to make this work is he reweighted the two samples so that they had the same effective distribution n of z. So there are some subtleties to making this properly, but this is really kind of one of our best estimates of whether or not we're accounting for noise bias properly. And these are, consistent with 0. So, right, with 2 bins.
So you said that didn't work.
this doesn't work. The mean shear binned by signal to noise doesn't work, but the mean shear around, tangential shear around lenses is not 0. And so then multiplying by 1 plus m would give you something. So the key is that you need to have something that had signal. And most of the things you can do just with a straight up catalog like mean shears don't give you a signal. You get 0, and so 0 times 1 plus m is still 0. So that's why we had to go to the tangential shear as something that does have signal.
So when you simulate your source sample by signal to noise, you also correct for selection bias?
Yes, so you need to be careful in the choice of your signal to noise ratio to make sure you're using a signal to noise ratio that's insensitive to shear, which most of them are not, and I will talk about that too, but that is a great caveat for this one. Yeah?
Can I ask you about the previous slide where it seems like you want to use your averages and not 0?
Oh, well, so there's an overall mean, which is just cosmic variance of the particular sample. So, you know, going to large enough scales, you expect it to be 0, but on any particular subset, we have enough galaxies that we can measure the mean shear on that subset to better than 1 sigma. So, yeah.
The previous slide, or the next slide, when I'm squinting at that, it looks kind of like oscillatory. Is that a real thing, or is that just if it is oscillatory, is that something real?
It's hard to say. It could be. There's a lot of, your brain's very good at picking up patterns, and a lot of times we've gone down trails of things that turn out that when you repeat it, you get a totally different pattern, and you're probably just your brain finding a pattern. But it could be. So it's always hard to tell with that kind of low signal to noise stuff, whether you're seeing something real or not. Melanie, yeah?
Are you counting any tests on simulation with or just?
So you certainly can. And so what did you have in mind? You're probably right. So.
I was going to say with signal to noise ratio, you can obviously simulate those things.
Right. So you can. So that's one of our key ways of calibrating this and trying to understand noise bias is by making simulations and seeing if and where we know what the true shear is and see if you get the right thing out. So, yes. But it's hard to design null tests for this particular one on the data. So, okay.
Someone mentioned adding noise. How does that work in practice?
You need a big enough field that's significantly deeper. So you want to understand your main field, right? Which means you need some fairly large field that's significantly deeper so you can degrade it. So you probably can't get the test to the level that you need it as a requirement, but it's very helpful for just kind of seeing, because then it's very purely a signal to noise effect. Like these other ones, you worry about, say, selection effects and these other aspects. So if you are seeing a problem, that's a great way to try to diagnose whether it really is just a noise effect. So it's probably not sensitive enough though to rely on that as your only test. Okay, this is the last example. I have one more fun one that I probably won't split you up into groups on. But so photo Z errors can be a function of seeing in the images, right? So there's the seeing changes, the magnitude errors change. So you get errors in colors and consequently biases in the photo Z estimates. So, whoops. I was too fast for you to see what the axes were. So design a null test to show that the variation in seeing does not adversely affect the inferred redshift distribution across the survey area. And I probably won't give you too much time, so think quick, and then I'll interrupt you again. Okay, who has an idea?
If you had some objects where you needed the spectroscopic redshift, you could look at the difference between that and the photometric redshift because it's a function of seeing the
Great, right. So a lot of times with photo Z questions, go to the truth, right? So for some subset of your objects, you have true spectroscopic redshifts, and you look to see if as you observe those objects in different seeings, whether you get the consistent answers or not. Great. Other ideas? Yeah. Oops. No. Anyone? Yeah. Great. Yes. So that's what Boris did here. So he took his, for several different photo Z codes, he looked at the distribution N of Z of the high seeing sample versus the low seeing sample and seeing if the difference was significant. So this one I find particularly interesting because it was designed as a null test. And after they made it, they realized that it's not actually a null test. So you actually expect for the high C sample for the distribution to be broader because your errors are bigger. So when you take the difference, you expect actually to get a little Mexican hat shape, right? The small seeing should have smaller errors, therefore smaller photo Z errors, therefore a tighter distribution, closer to the truth probably, whereas the other one should be slightly wider. And so you can kind of see it. There's kind of an up and down and up pattern to some of these. There's also a lot of other shapes in there, so there's clearly some real things going wrong in some of the cases. And then they did this both on real data and on simulated data that was designed to kind of mimic many of the properties of real data. And they also see it over there. So sometimes when you design a null test, when you're trying to understand it, you realize that you didn't actually design a null test. And, any other ideas? Okay. So this last one, I'm not going to have you divvy up. I'm just going to solicit ideas so you can think of it. But when I was looking into writing this lesson, I came across a paper that talks about one of the very first null tests, at least that were described as being a null test, a null value experiment, I think it was called. So it's a test of Coulomb's law. And specifically that the Coulomb's law, the power, the 2 in Coulomb's law is really 2 and not some 2.0003, whatever, some epsilon different from 2. So who can think of a test that would be a null test that exponent really is 2 and not something else? Gauss's law, what do you mean? You spoke too soon. Who can come up with it before Robert gets his brain around it?
The shell theorem depends on it being particles too.
Right, so describe the shell theorem. What do you mean by that?
That if I have a spherical distribution, it acts as though it's a point charge everywhere.
Okay, so what experiment could we do with that? How could we make a spherical distribution to test that?
Well, you could,
Who's closer to Jackson than these gold guys? Charge on a conducting sphere, excellent. And what should be the test then?
I guess the size of the sphere doesn't matter.
Well, what's the measurement though?
You look at the force from the charge potential on the inside.
Close. Yeah. The charge, you measure what? Well, how do you measure a potential? There's no field inside. That's right. So you make a spherical conducting device, put some charge on it, and then measure the electric field inside the sphere. So this is basically Faraday's law kind of experiment, right? Well, right. So you can see there's a tiny little thing. Oh, I have a pointer, right? Here we go. Hole with cap for connecting spheres or electrometer. So if it's a small enough hole, it shouldn't violate the principle that the charge is spread equally and you should still get no electric field. That's right. here's a picture of the actual device, which I thought was kind of fun. And then here's their the text from their paper. Let D be the largest deflection which could escape observation in the first part of the experiment. Then we know that the potential in the globe at the end of the first part of the experiment cannot differ from 0 by more than this small number as a fraction of the voltage. Anyway, so by doing this, they concluded that the power law index differs from 2 by no more than about 1 in part in 20,000, which is pretty cool. And so the reason he designed the experiment this way, and the reason it was the most sensitive proof of Coulomb's law at the time, is that he described kind of 4 kinds of devices, right? You can imagine a measurement device that is precisely calibrated and it tells you exactly the thing that you care about, say the electric field or something. You can imagine something that isn't precisely calibrated but it's linear, so you know that if it measures twice as high of some reading, the real value is twice as high, so that would be a linear device. You can imagine then not quite as good, a monotonic device that, it's not really linear, it's got some weird function, but it's monotonic. So if it measures more, then the electric field was more. And then the worst kind of device is one that just measures the fact that there is some field, but can't really tell you anything about its magnitude. And he was saying most of the electric device measurement devices were of that last category. And so the only really sensitive measurements were ones that relied on yes or no questions. And so this was the most sensitive test of Coulomb's law for quite a long time. Okay, so now I'm just going to go through a list of caveats. Some of them we've already mentioned, but so first, if you fail a null test, quote unquote, that doesn't necessarily mean you're screwed, right? Your science might still be okay. Like this null test may not tell you much about how important that systematic error is for your science, right? So what you need to do is always propagate through if your systematic error has some level and you've estimated it through your null test to be some amount, how much does that affect your final science? And that could be much smaller than your statistical errors, and in which case you don't care. So here's an example. These are what's called row statistics, which is basically a quantification of that whisker plot you guys saw, which is the correlation of the residual PSF pattern. And you can see it's measured to very high signal noise. These blue points have error bars that are much smaller than the signal. But the yellow is our estimated requirements of how that would affect cosmic shear results. And so even though this is failing the null test, so to speak, it's not failing it egregiously enough for us to be too worried about it. So it was always below the yellow slope. Conversely, if you pass a null test, that doesn't mean that your systematic error being tested doesn't impact your science, right? It's hard to design some of these null tests, right? Some of these null tests may not be very sensitive to the systematic in question, and maybe in particular less sensitive to the systematic than your science is. So you need to kind of really think about the relative significance of the null test versus your science in both directions. We ran across this before. So sometimes things you think are null tests are not really null tests. So when you fail a null test, sometimes you're trying to understand what's going on, and you may realize that, oh, this is actually not something that's supposed to be 0 for some subtle reason that didn't occur to me. Here's a really fun example. So this is galaxy lensing results. So the blue curve is probably should say preliminary across it. I apologize to Carles and Judith for that. But so this is tangential shear around, I think, galaxies or something, some kind of lenses, right? And they said, well, stars shouldn't have a tangential shear, right? Stars should just, they don't know anything about these lenses. So what if we looked at the shapes of stars and called them sources? Pretended that they were behind these lenses and see what happened, right? Because they're obviously not behind the lenses. And it's mostly flat, but at large scales, it goes significantly negative. This is a relatively high signal to noise estimate that it's non-zero. And at first I was like, what's going on here? It turns out this is just a correlation between the shape of our overall mask of our survey area, and the fact that at the edges of the mask, the PSFs tend to be on the edge of the field of views, which have larger shapes and tend to be kind of oriented along the edge of that mask compared to the average in the middle. So at large scales, you get around random points within your field, you tend to see those kinds of patterns at large scales rather than the opposite kinds of patterns. And so it gives you a slightly negative tangential shear pattern. And the way we kind of confirm that is, or at least that it wasn't anything connecting to the lenses, is that you get the same thing when you go around random points. So it didn't matter that it was lenses versus random points. You know, the stars still didn't actually know that they were lenses or not. But tangential shears around anything do show this kind of a pattern for kind of a subtle reason. Another caveat, this was one that Robert brought up. If you fail a null test, it might be due to something other than the thing you thought you were testing. Right? These things can be fairly subtle, and there's lots of things that kind of correlate with each other in subtle ways. So when you have a failure, it can be tricky to figure out why you're having the failure, and it requires often simulations and other creative ideas of how to test various hypotheses to figure out what is causing it and then hopefully to fix it. Here's an example fairly recently. So, sorry, what? Okay. So fairly recently, this is for Y1 shears, and for the Medi-Cal method, we were seeing a correlation, a negative correlation between the galaxy shapes, that's on the y-axis, and the PSF shape. So you've seen versions of this, right? And there's a significant correlation here. And we ran tons and tons of simulations of complicated PSFs, and Medi-Cal always got 0 on the simulations. It was never there was never any leakage, and certainly not negative leakage, in any of our simulations. And eventually we realized that this is all due to the PSF modeling errors, and it just happens that the magnitude of the PSF shape is correlated with the magnitude of the error in the PSF shape. And so, of course, PSF modeling errors leak into galaxy shapes because they can't not. I mean, that's just how, you get the PSF wrong, you're going to get the galaxy shape wrong in the same direction. And so this is just a second order correlation of the galaxy shapes with the PSF modeling errors, which we did understand, and we had other tests of that we knew about and knew that was a systematic, and we had ways of accounting for it, but we didn't realize that this was the same thing. Selection effects. So selection effects can really mess you up. During the SV analysis, we ran into all kinds of problems with selection effects, and I think now we mostly understand them, but it's always very, very subtle to get these right. So here's an example here. This is our first effort at looking at the mean shape versus signal-to-noise ratio. This is the one that I said does not actually test noise bias. But at first we said, oh, well, there's something going wrong. We're getting these really big biases at low signal-to-noise. Well, it turns out those big biases, and you can see there's the opposite bias all the way on the far end. The last point is high, the first point is low, everything else is actually not too far off from 0. And this is entirely due to selection effects. So our definition of signal-to-noise ratio at this point was something that was not shear independent. So sheared objects were systematically different in their signal-to-noise estimate than not sheared objects. And so at the first bin and the last bin, you get a selection effect. And in fact, every bin in between, you also get selection effects on both sides. Turns out for most of them, they canceled. But on the first and last one, there's nothing to cancel with it, so you get the effect. Here is how we investigated that. So the simplest signal-to-noise ratios, you just add up the signal and all the pixels and divide by the noise. It's a really terrible signal-to-noise estimate. And you can see it's a much lower signal to noise than any of the rest of these, but it also is completely insensitive to shear. So that's flat. You get the same value no matter what shape your galaxy is. Most of the rest of them, so this was the one that we had been using. I'm not going to go into the details of what they mean, but this was what we thought was a good idea, is how Gaussian, for instance, defines signal to noise. And you can see there's a slight fall off, and that slight amount is enough to matter for causing biases like this. So we tried a few other ones. There's a circular aperture. Here's if you don't actually use the flux for W and just use W squared. This is if you just define, like flux divided by some noise is kind of a more direct estimate of signal and noise and divide them. That one's really terrible. The one that we ended up using is the flux divided by this, we call this the shape the galaxy would have had if it were round. So T round, so T is the size actually. So the size that the galaxy would have had if it were round with some, that's 2 pi r kind of thing. And so that's the noise inside some, roughly spherical shape, but not the actual size of the galaxy. It's the roundified size of the galaxy. And that one actually ended up very, very flat. So this is the signal to noise we ended up using. We call it SNR sub R, signal noise sub R, so the roundified signal to noise. And all of our cuts for the NG mix code were used this guy. But this is the kind of thing that Rachel was talking about. You need to be very careful about what signal to noise and size and such definitions you can use if you're going to cut anything on them. And that includes in your null test where every bin has a cut on both sides. Right. And the last one, so passing all of your null tests. You have this huge suite of null tests, and you pass them all. Great. So that doesn't mean you don't have any systematics. So first, it's hard to come up with null tests, as you saw, right? It can be very tricky to come up with good null tests for some of these systematics, and certainly ones that are sensitive enough to really test what you care about. And then there's always the Rumsfeldian unknown unknowns. If you haven't thought of a particular systematic, you may have no tests that test for it, and they may still be in your data, and you just don't know. So that's always the issue. So don't get too confident once you start passing lots of null tests. This is just a summary of what we learned today. So first, null tests are an invaluable tool. You should all make null tests for as many things as possible. Designing good null tests is a bit of an art. There's not kind of a straight up prescription of how to do it, but it's something that you should all practice and try to get good at and figure out which null test would be appropriate for the science that you're working on. And then once you have results, interpreting them is also pretty tricky. And you always have to worry that you may actually have a problem with your test rather than your data. For writing code, I have a mantra that half of all bugs are in your test suite. That's probably not quite true in null tests, but you always need to be aware of the possibility that you may have an error in your test rather than in your data. So, thank you.